Quest to see deep inside matter. In this video, I will try to explain matter and its subdivisions, giving special thrust to nuclear matter, that is, nucleus, its subdivision, nucleons, up to a brief introduction to quarks.
Size does matter. As we move from atomic physics to nuclear physics to particle physics, the length decreases and the energy of exploration increases. In atomic physics, the length is of the order of angstrom. In nuclear physics, it is of the order of few Fermi, and in particle physics, it is less than 1 Fermi. Here goes a simple picture of matter and its subdivision as we move away from crystal up to subnuclear particles. How does the size decreases? As the size is very small, we cannot see what is happening inside an atom or even a nucleus by a very high power microscope even. So the exploration depends mainly on indirect experiments like scattering and indirect observation like through spectroscopy, that is through spectroscopic analysis, or by study of their radioactivity, maybe natural or artificial, and based on all the data and information we receive through them, we try to accumulate all the information and construct some models like atomic models, like nuclear models. As I have told earlier, atomic physics and nuclear physics have their specific range of size, that is dimension and energy. Here energy is expressed not in joule but in electron volt. In atomic physics it is of the order of electron volt, in nuclear physics it is of the order of million electron volt, and in subnuclear physics, that is for particle physics, it is of the order of gillion electron volt or GeV. This is a very simple picture of an atom visualization, and the size of the atom is here of the order of angstrom, and nucleus occupies a very tiny part of the whole atom. As we move on from atomic to nuclear physics, there appear some very fundamental few questions. Number one, what are the constituents of a nucleus? The general answer is nucleons, that is the neutrons and the protons. This is the generic name, because inside a nucleus we cannot distinguish that between a neutron and a proton. Secondly, what are the forces that keep the nucleons bound together? Obviously the answer is nuclear force. We'll come to this point later. And lastly, how are the nucleons bound together? The answer is, for that we construct nuclear models. As I have told earlier, the nucleus is much smaller than the atom as a whole. As the atomic scale is of the order of angstrom, the nuclear scale is of the order of Fermi, that is 10 to the power minus 15 meter. Most of the mass of an atom is concentrated in its nucleus because electrons revolve around the atom outside the nucleus and they carry a negligible mass of the whole atom. This is evident from this relation that mass of a proton is 1836 times that of an electron. So electrons carry very negligible part of the mass of an whole atom, and the most of the masses are concentrated inside the nucleus. The nucleus occupies a very tiny part of the whole atom, and the dimension of the nucleus is generally obtained from the relation R is equal to R naught into a to the power 1/3, where R0 is a universal constant which is 1.2 Fermi. A is obviously the mass number, and this density is universal and which is of the order of 1.4 billion metric ton per inch cube. This density is very high. This density is almost near to the density of a neutron star. So the point is, nucleus occupies a very small part of an atom, but it is highly dense. So the question is, inside such small region, how such a dense matter can be contained in a bound state? This is very fascinating. There comes the fascinating nature of the nuclear force. It is charge independent, it is mass independent, so that we cannot distinguish between a proton and a neutron inside a nucleus, and that's why inside a nucleus they are having a generic or common name, that is nucleons. Nuclear force is short range and it saturates at the surface of the nucleus, that is exists only inside a nucleus. It is always attractive in nature, but it is spin dependent. That's why we are having different forms of hydrogen, different isotopes of hydrogen like orthohydrogen, parahydrogen. So protons and neutrons, that is nucleons, are the constituents of a nucleus, and these protons and neutrons are not indivisible. They are composed of more smaller entities which are called quarks. There are 6 varieties of quarks, that is up down, strange charm and top bottom, and protons and neutrons are generally composed of up and down quarks. There goes the quark composition of the nucleons. A proton is composed of 3 quarks, 2 u quarks and 1 d quark, and a neutron is composed of 2 d quarks and a u quark. Mind it, here the dimension scale is of the order of Fermi, that is distance scale is of the order of Fermi, and the energy scale is of the order of GeV. The voyage of mankind to see deep inside matter is very, very, very fascinating. As we move from crystal to molecule, from molecule to atom, from atom to nucleus, from nucleus to nucleons, we find that still the matter is not indivisible. And the nucleons are composed of still smaller entities. Those are called quarks. Thanks a lot.